This is an experimental recording of the lecture of Statistics 2. Our subject today will be multiple linear regression, and we will start with deriving some useful formulae. So what is our problem? We have a bunch of variables. The first is x1, and this will be our dependent variable. And we have r minus 1 independent variables. We start to number them from 2. So there is x2, x3, up to xr. These are independent variables. The dependent variable is treated as a true statistical variable, and variables from x2 to xr are treated as data, so there is no really random effect here. Our model says that variable x1 can be calculated as an affine function of variables x2 up to xr. So there is some coefficient, free coefficient b0, and there are directional coefficients b2 x2 plus b3 x3 up to br xr, and some prediction error, which is assumed to have normal distribution with average equal to 0 and some unknown variance sigma square. The variables from x2 up to xr are not treated as random variables. They are just the data. They encode an information about elements of population or elements of the sample. However, they do not have any random qualities. The only random variable here is the variable that we are trying to predict, variable x1. So this is the true statistical variable. So we think in the following terms. Our population is divided into subgroups by values of x1, x3 up to xr. And in each subgroup, x1 behaves a little bit differently. We assume that the mean value of x1 depends in an affine way on the subgroup, so on the values of x2 to xr, and there is some variability which is due to some factors that are not taken into account by independent variables, and this variability is hidden in the error. So in each subgroup, x1 variable also has normal distribution with mean value depending on values of independent variables. However, the variance will be in each subgroup, the variance is the same. As previously, we are looking for values of the coefficients that are such that the sum of squares of error is the least possible. We can do it hypothetically in the whole population, but what we usually do, we select a sample and we look for estimates of these numbers, which are appropriate coefficients calculated in the sample. We are now passing to deriving formulae for estimates of B0 up to BR. So the function that we are trying to minimize is the following: sum of squares of errors. This sum of squares of errors is treated as a function of the coefficients up to BR, and since we are looking for estimates in the sample, we will add hats to those numbers. And the function is as follows: we have to make a sum over all elements of the sample. So here we have a number of elements in a sample, and we calculate a square of an error, which means that from the actual value of variable x1 from the element of the sample with number I, we subtract the prediction, and the prediction is B0 minus B1 times B2, sorry, there is no 1 here, B2 multiplied by the value of x2 for the element of the sample with number I, and the same goes for the other variables. So up to BR XR calculated for element of the sample with number I, everything squared, everything summed up. So this is a quadratic function of variables B0 up to BR. When we want to find the minimal value of this function, we have to calculate differentials with respect to variables, and then assume that those differentials are 0. We get a set of equations from which we are able to determine formulae for this point when the minimum is realized. So let us first differentiate with respect to B0. The SSE differentiated with respect to B0. B0 is here, so we see that the derivative will be minus 2 times the sum of sum over I, not n, sorry, of the whole bracket but without the square. So I repeat this thing. Great, and this has to be 0. So what do we do? Since it has to be 0, we can forget about the numerical coefficient here. We just can cancel it. And then both sides of the equations, this is one side of the equation, this is the other side of the equation. So both sides of the equation we can divide by the number of elements of the sample. And take a summation. So this means that, for example, say from this part I will have 1 over n sum of x1 of omega I, and I sum over all elements of the sample. So what I get is just the average value of x1 in the sample. And the same happens for other coefficients here. So as a result, I get the following, I had the following condition. The average of x1 minus b0 minus b2, the average of x2 minus br, the average of xr has to be 0, which means that my b0 can be written as x1 minus b2 x2 minus br xr. So this formula says that a point with coordinates being sample means of all the variables belongs to the graph of my regression function. So this is something we save for later. We will use this formula soon. Now we differentiate our sum of squares of errors with respect to some other coefficient, say b k. The result is similar. We again have minus 2, but this time we have to multiply. We have the same bracket as previously, so maybe I will not just copy it. I will not rewrite it. I will copy it. It will be faster. Yeah, it is here. But since we have differentiated with respect to some coefficient which is multiplied by a variable, that means that we have to put this variable somewhere here. So xk of omega I. Again, the condition is that this whole thing is 0 equals 0. Again, I can cancel this coefficient. Again, I can divide by n, do the summation, and as a result I get 0 equals an average of x1 xk. I will use this symbol E of expectation value or average instead of a bar because either, of course, I am in the sample, but I would have to, I don't know, put bar over two variables, and then we do not know whether it is just an multiplication of the two sample means, or it is just a mean value of variable which is a multiplication of two variables. Therefore, maybe it will be easier to write it like that. Then there is minus b0 hat, and again I write average in an expectation value, this time of xk, and the rest of the bracket, which is b2 expectation value of x2 xk up to BR expectation value of XR xk, again calculated in the sample. Now I will use the formula for B0 and put it here. This means that I have to be a little bit more refined by writing while writing things. So let me make it bigger, and then I have 0 equals expectation value of x1 xk minus, and now the formula for B0. The formula for B0 using again expectation value instead of a bar. So there will be E1, not E1, E of x1 minus B2 E of x2 and so on up to BR. B0 multiplied by the expectation value of x k, and then I write down the rest. The rest is here. So it is minus B2 expectation value of x2 xk minus up to BR expectation value of XR xk. And now I'm starting to introduce some order to this formula. So for example, let us note that taking this thing, and this thing, we get a covariance of variables x1 and xk. So let us write it in blue. Covariance of x1 xk. And then we keep track of the coefficients of those b's that appear here. For example, in front of B2, we should remember also this component. So in purple we write plus B2, and there is expectation value of x2, expectation value of xk minus expectation value of x2 xk, which is a covariance of x2 xk with minus sign. And the same can happen for all the coefficients up to r. Therefore, in white, I can finally write that 0 must be the covariance of x1 xk minus B2 covariance x2 xk minus up to BR covariance x2 xr. Such an equation I get for I equal 2, 3 up to, for k, sorry, not I, for k equal 2, 3 up to r. Which means, as a matter of fact, I have r minus 1 equations. I can then use my algebra skills and write those equations in the form of a matrix equation. I will have the coefficients will form a covariance matrix on the diagonal, the covariance matrix has variances. And off-diagonal matrix elements are symmetric, and they are just covariances. So x2, x3, up to a covariance x2, xr. Here I will have a covariance x3, xr. Here again, a covariance x2, x3, covariance xr, x2, and probably here should be also written, a covariance x3, xr. Yeah. So this is the square matrix of covariances of independent variables. This matrix multiplies our unknown quantities from B2 up to BR, and on the right hand side I get the free components. The free components were these. These are covariances of the dependent variable with independent variables. So this is the covariance of x1, x2, covariance of x1, x3, up to the covariance of x1, xr. Now we have a matrix linear inhomogeneous equation. We have solved it, for example, using the Kramer formula, Kramer method. For that, we need a determinant of the whole of the main matrix. So D will be the determinant of the covariance matrix with AJ starting from 2 up to R. And we will also need determinants of such a matrix with that looks similar to this main covariance matrix, but the kth column is replaced by the free this right hand side column. Therefore, dk determinant will be the determinant of the following form. For simplicity, I will denote C of xi, xj by just Cij. These are symmetric coefficients. So here I have C2, 1, C2, probably I should use some order, because otherwise I will be confused. So here is C22, C23 up to C2R, then C32, C33 up to C3R, and then at some level K there will be, instead of CK2, there will be C1, 2, C1, 3, C1R. And then I go to the end with C2R, C3R, CRR. Okay, so this column is put here in the position K, and we get this determinant. Provided the main determinant is different from 0, we get the formula for B's. So BK is DK divided by D. To make things maybe a little bit more homogeneous, I will use the full covariance matrix for the full set of variables starting from 1. Here, as you can see, we start from 2, we go up to R. So what I will need in the following is the matrix, the full matrix C, which will be C11, C12, C13 up to C1R, C21, C22, C23 up to C2R, and so on. Let me use a little bit of your patience and write this down, say once here, up to the very end, CR1, CR2, CR3, CRR. Okay, so this is our covariance matrix. The main determinant is calculated from this matrix. Therefore, we can write down that D is an algebraic complement of the element C11 of the full covariance matrix. I will write C11, and when indices are up there, it means that it is an algebraic complement. Algebraic complement of an element C11. And then let us analyze the problem with decay. What's decay? If I want to have decay, what I do, say k equals 3. So what I do, I remove this column and I put the first column in this place. So technically, I can think in the following manner. I remove this column, this row and this column, and calculate a determinant of what is left. It is again an algebraic complement of this element up to a sign. So dk is plus or minus, we will determine it in a moment, of the algebraic complement of C of C1K or K1. This is mostly the same because the matrix is symmetric. Now there is a question of what sign should be written here. So first of all, we have to remember that algebraic complement includes a sign. So algebraic complement is not just the determinant of what is left, but determinant multiplied by a sign, and this sign is -1 to the power number of column and number of a row. So in this case, this thing also includes -1 to the power k plus 1. So this is one thing. If we want just the determinant, we have to put this sign into the formula. And another problem is that here, when we calculate the algebraic complement, this column that should be put in the position K is in the first position. Therefore, I have to put her, I have to switch order and put this column in the right position. The number of changes that I have to do equals K minus 2. I can see that, for example, if K equals 3, I have to make 2 changes, which means what I get is K minus 2 sign. Finally, dk is minus 1 to the power K minus 2, then minus 1 to the power K plus 1 to cancel the internal sign of the algebraic complement. Finally, this is just minus CK1. So I have the general formula for BK. It is minus C1K divided by C11, and this K is bigger or equal to. And we also remember that we have calculated B0 previously. We can find the formula. The formula is here. We can put it back in our slide here. Okay, and these are full formulae for our coefficients of the multiple regression. Now we can draw some conclusion out of our calculations. First of all, the calculations are valid when this C11 is not 0, which means that this matrix here has a non-zero determinant. What does it mean in terms of our variables? No, it means that one of the columns is a linear function of the other columns, or it also may happen because this matrix of this covariance matrix can be treated as a symmetric bilinear form on the space of variables. However, it is not non-degenerate. It is positive definite, but this is not non-degenerate because there is a kernel that consists of constant variables. So the variable that has the same value for each element of the sample definitely belongs to the kernel, and I calculate a covariance with whatever other variable, I will get 0. Therefore, vanishing of this determinant means that one of the variables is an affine function of the rest. So let us write this down because this is an important information. D equals C11 equal 0 means that one of the variables, say Lth, is an affine function of other variables. Therefore has a form xl equals some number alpha plus b2x2 plus beta 3x3, up to L minus 1. And then we resume summing from L plus 1. And we sum up to R. Therefore, we shouldn't do multiple regression in case when we have an affine or linear dependence between variables that are giving us information about our population. Then next thing, after calculating our coefficients and determining the equation of regression, we can ask a question whether there is a strong dependence between dependent variable and independent variables. To measure the strength of the dependence, we as usual compare the error without using the additional information with the error using the information of independent variables in the form of linear regression. So assume we have calculated the regression. We will denote this function by x1, and after a vertical line we list all independent variables. This is b0 plus b1 b2 x2 up to br xr. So the estimate of error, if we don't use this information, is the total sum of squares, which is just sum over all elements of the sample of the difference between actual value of x1 and the mean value of x1, or rather sample mean. Squared and summed. And the estimate of the error, so SSE, the thing that we have just minimalized. So after being minimalized, it is a sum of over all elements of the population of x1 of omega I minus the prediction calculated for the ith element of the sample, squared and summed. Our measure of dependence is constructed as usual. This is a coefficient r squared. When we list whatever variables we use, so there will be 1, 2, up to r, and what we have is SST minus SSE divided by SSE. As usual, there are some relations between different sum of squares. So what we got here, it is sometimes denoted by SSM. This is sum of squares of the model, and sum of squares of the model is given by the following formula. Again, sum over all the elements of the population, of the sample, and it is a difference between the prediction with using our additional information about independent variables and sample mean of x1 squared and summed. And as usual, we have this relation SST equals SSM plus SSE, which means that R can be also written as SSM divided by SST. So this is for the descriptive statistics. We can measure how much information we gained by using rather regression as the prediction of our value of variable x1 than just the mean value. Another question is whether this result is statistically significant. This we can check constructing the usual Fisher-Snedeker variable f. So for statistical significance, we write down f, which is as usual SSE divided by SSM up to the numbers of degrees of freedom. So degrees of freedom of, sorry, it is just another way around. SSM divided by SSE divided by the number of degrees of freedom of the model and number of degrees of freedom of the error. The number of degrees of freedom of the error equals numbers of element of the sample minus number of estimated parameters, which is number of independent variables. This is r minus 1, and then there is still one more estimated parameter, which is this b0. Yeah, so these are all those b's. These are all those b's from b1 to from b2. Sorry, from b2 to br. There is r minus 1 of them, and this is coming from b0. So at the end we have n minus r, while the number of degrees of freedom of the model is the number of independent variables. The Fm number of independent variables is r minus 1. And then we do the usual, we choose the significance level, we check whether the value we obtain is statistically significant. So these are the calculations. Next recording, next short lecture will be about the example. When we take the particular data, we calculate, we look what are the relations between different coefficients that we obtained, and how we can improve our prediction by using additional information in the form of linear regression with more than one variable. So this is that for now. Thank you.